Hello, my name is Joshua Green, and this is Lab 2 for Physics 2212 on calculating the magnetic field of a permanent dipole magnet. The main goals of this lab were to measure the distance dependence of the magnetic fields using on and off axis measurements through a bar magnet, which served as observed models, observe the relationship between the magnetic field and various observation distances by applying Lorentz-Savart law, and creating computational models using the calculated magnetic moments from the observed model to determine theoretical results. A brief overview of the results were that n was calculated to be 3.24, mu was calculated to be 3.24 ampere meters squared, and the theoretical magnetic field was at 45 degrees was 8.75 times 10 to the negative 6 teslas, and the observed value was 1.69 times 10 to the negative 5th teslas. Key principles include Lorentz-Savart's law, which illustrates how each infinitesimal segment of current contributes to the total magnetic field at a point in space. Distance dependence, which explains the relationship of how the strength of a magnetic field decreases as you move farther away from the magnet. On-axis magnetic field, which refers to the magnetic field along the axis of the magnetic dipole, or in this specific experiment, along the length of a bar magnet. And off-axis magnetic field, which refers to the magnetic field at points not along the axis of the magnetic dipole. So the first part of the experiment was to determine the power of the distance dependence on axis through using a magnetometer app. The system was the magnetometer sensor, and the surroundings were the Earth and the bar magnet. Assumptions were that the magnet can be treated as a magnetic dipole, the phone is consistent with measurements, and that nothing interfered with the magnetometer besides the bar magnet. And the procedure included rotating the phone on a flat surface until the X component was very close to 0 teslas, and marking locations along the X and Y axes with tape. Then the distance dependence was found on different magnitudes as seen in this picture. Based on that information, a line was formulated as seen here, and that was used to determine n and calculate the magnetic dipole moment, or mu. And I did this by setting the on-axis dipole moment equation equal to the KRN equation and solving to get 3.24 ampere meters squared. I then used a similar procedure for the on-axis experiment but off-axis and found the dperp, which is the distance from the bar magnet where the net magnetic field is around 100 microteslas. I then positioned the sensor at a dperp location in X and Y direction from the bar magnet and recorded the X and Y values from the magnetometer app at the location. I then corrected the Y value by subtracting the Y component of the Earth magnetic field and did the entire procedure 3 times to find the average distance and the average magnetic field, which was determined to be 0.313 meters and 8.75 times 10 to the negative 6 teslas, respectively. From here, I then used the starter code provided in the lab experiment and inserted my calculated magnetic dipole moment, or mu, which is 3.24, and created a function for the magnetic field. I also created 2 observation locations on axis and 4 off axis, and arrows that represented each observation location respectively. I then created an observation location at 45 degrees off axis and used magnetic field function to create an arrow. Here are the results. The orange arrows represent the on-axis observation locations, the blue represents off-axis observation locations, and the purple arrows represent the 45 degrees off-axis location. The magnitude was computed to be 1.678 times 10 to the negative 5 teslas, which differed greatly from my observed location, observed calculation. And this could stem from other magnetic fields being present during the observed model calculation, such as my computer and tablet, and human error in measuring using a ruler, and a possible faulty magnetometer app. If I didn't compensate for the north in the beginning, there would have been an interference with Earth's magnetic field, and thus would have been a combination of both the Earth's field and the bar magnet's field, which would have made it even more difficult to isolate the contribution from the bar magnet alone. Additionally, the values would have been skewed in the direction of the magnetic north, and theoretical and experimental values would have been even more different. And if I used two identical magnets stuck end to end of this experiment, the magnitude of the magnetic field would have been two times stronger, and but the direction would have stayed the same.